distinct pleasure to introduce Professor Xiaofan Wang, who's distinguished professor at Shanghai Jiaotang University, and he's also deputy dean of one of the colleges of that university. And Xiaofan has had a long and distinguished career looking at dynamical processes on complex networks and control interventions. He has received numerous prizes over the course of his career. He's written several very important books, one on an introduction to complex networks, and another one more recent on pinning control in complex networks. And he's going to focus today on competition dynamics, which is an interesting area we haven't heard so much about yet. And I also want to mention that amongst the numerous activities that Professor Wang leads, he's also the chair of the Chinese Committee on Complex Networks, which is an organization with more members than we have at our conference today. And he's also our brave leader organizing NetSci X 2018 in Hangzhou, China next January. Thank you.
Thank you, and thanks, Reza, for the introduction. And I'm very glad to have this opportunity to share with you our works on competition. And I'm also very glad that Cesar just showed you a lot of research on China. So as Reza mentioned, NetSci X will be held in a very beautiful city, Hangzhou, China. So you'll have a good chance to see if Cesar tell you the truth, right? Yes. As you may all know that both cooperation and competition are very common in real world, such as in ecological networks, brain networks, and economic networks, which are exactly the themes of the three previous talks this morning. Here, I'll show you, I'll start from a very simple but very classical example, which I believe you all know, that's the Karate Club network, right? And in this network, during the observation of this network in 1970s, there had been a competition between the instructor and the manager of the club over the issue of rice. And the instructor wished to raise the rice while the manager wished to stable the price. So eventually, the whole club divided into two communities, as we all know. One community supported the instructor and another supported the manager. So in recent years, we also all know that this network has become a very famous benchmark example of community detection comes in networks. During my preparation for this talk, I happened to find a photo I took 3 years ago. I remember Professor Porter just received the ER prize, right? Yeah, on NetSci 2014. The reason for me to take this photo is that Porter mentioned, I would lose my community detection card if I didn't use this example, right? However, my focus today will be on these three questions. The first one is that, can we provide a dynamic model to show the competition process in complex networks, such as in the club network? Can we simulate how opinions of members in this small size network evolve such that eventually they were divided into two communities? That's the first question. The second question we wish to answer is that, can we predict which competitor will be the winner just based on, for example, the positions of the winner in the network and the network structure? And the third one is that, which is about optimization. For example, suppose that I'm a competitor, I wish to add some links in the network, how to add these links so as to, for example, maximize my relative influence in the network? That's the three questions we would like to answer. So let me start from the first one. We proposed a very simple model which consists of just two competitors. They have fixed yet different companies which we set up just simple 1 and -1. And also, we assume that all the other agents in the network are rational agents, which means that they try to update their opinions, their states, based on the states of their neighbors. And this algorithm, in fact, is very popular in control theory, which called consensus protocol, which means that each agent tries to be similar to its neighbors. Okay, with this very simple model, we can prove that on the very mild assumptions, the states of all the normal agents will eventually converge to a steady state, which is fully determined by the network structure and the positions of the competitors in the network, which is unrelated to the initial condition. So with these theoretical results, and we can define the competition result. That is, if eventually a normal agent has a positive value of state, then we can say that this agent will support competitor I, and on the other hand, a negative value corresponds to support competitor J, and if it's happen to be exactly 0, it will be an abstainer, right? And by calculate how many support I, how many support J, we'll see which one is the winner. So the model itself is very simple. Okay, now we try to apply this model to the karate club network. We fix the states of the manager and the instructor at 1 and -1. And we randomly choose the initial states of all the other members. And we update those states according to this very simple algorithm. So that shows, let me see, oh, sorry. And eventually, the whole network will converge to a steady state. And to no surprise, in the steady state, the whole network divided into 2 communities, which exactly match the real situation. Here, one group corresponds to positive value of state, and other group corresponds to negative states. Okay, and furthermore, we can judge the degree of supporting of each agent towards its corresponding leader based on the absolute value of the states. For example, here I'll just give you one example. Node 9 has a very small absolute value, which means that it's a very weak supporter of the manager, and which is indeed the case if you have a look at the original paper. So this very simple example shows that although our model is very simple, perhaps it provides some reasonable mechanism behind some competitions in computational networks. But unfortunately, we do not have other real data to show how universal this model is. Okay, so that's the first model we proposed. And now, based on this model, we would like to solve the second question, which is the window prediction. To solve this problem, we proposed the influence matrix. This matrix is not a new matrix which has been investigated as well, such as in network reconstruction. Here, the basic idea is that if there is a direct link between 2 nodes, we could define the strength of influence use a parameter ender, right? And if there is a length of path 2, we can define the strength of influence as ender square. right? And so in this way, in fact, we could have such kind of influence matrix with each element characterize the mutual influence between a pair of nodes. Now the problem becomes, can we predict the competition result just based on the network structure, just based on the influence matrix? Okay, to do so, we could define that given two competitors for the normal agent K, we could compute this difference. If this difference is positive, then we could say that agent K will support competitor I, otherwise it will support competitor J, right? So we use this criteria to try to predict the competition results in our dynamic model, And we apply this criteria to the quadratic club network, which shows exactly the same result as the real situation. Okay, to show the effectiveness of this criteria, we selected a number of social networks. Of course, in this social network, we do not have those real competitors. So what we did here is that for each network, we choose every pair of nodes as competitors. And we calculated the average results. We try to apply the influence matrix criteria to predict which winner will win by compared to the dynamic model. And here's the result for 8 undirected networks, which shows the success rate of competition. We also did a large number of simulations on some directed networks. And in general, on average, we could show that in both cases, the influence matrix criteria could provide more than 8% accurate of success rate of prediction, which shows the effectiveness of this criteria. Intuitively, we may ask, for example, in the quadratic club network, the manager is the winner. Is it because the manager has higher degree than the instructor, or is it because it has higher opportunities than the instructor, right? We could have a number of centrality index to compare. So we have such kind of centrality-based criteria, which states that a competitor with higher centrality might win the competition. So we'll check which index is the best one to predict competition result in this competition model. And we applied this centrality-based criteria to a number of undirected networks, and we found that in most cases, causal centrality is the best way to predict which competitor will be the winner. And in all the directed networks we simulated, we found that the PageRank criteria is always best, which means that a competitor with a higher PageRank value would be very much likely to be the winner. Okay, if you have a look at these 8 criteria, we could divide them into two classes. For the first class of criteria, we could see a common point here is that in each of these cases, the importance of a node is related to the importance of its neighbors. We found that such kind of criteria provide better prediction results compared to degree, betweenness, casual, and closeness. So that's the main finding for this criteria. Now we move to the third question. Suppose that a competitor could add some links in the network. How to add these links so as to maximize its influence in the network. To do so, we need some mathematics. In the original network, we have such kind of formula for the steady state. By add some new links in the network, and we have a formula to calculate the new steady state. And with this mathematics, we could formulate two optimization problems. The first one is that the competitor try to maximize its number of supporters by adding a fixed number of new links, which is the constraint of this optimization problem. The second problem is that the competitor try to maximize its total degree of supporting by adding a fixed number of new links. Mathematically, the only difference between these two optimization problems lies in the objective function. Here you can see that we have a sine function, which we know is non-differentiable. And for this function, it's a smooth function, right? And right now, we enter into the theoretical computer science. Theoretically, we prove that problem 1 is NP-hard, is an NP-hard problem. And we conjecture that problem 2 is also NP-hard, but we still cannot have a rigorous proof of this problem. But good news for problem 2 is that due to some very good properties of this objective function, we could also prove that we can have a very good approximation solution for this problem by just using the very simple gradient algorithm. So that's good news for problem 2. Okay. So till now, we just use the very basic model, which constitutes just 2 competitors, right? And we use the very simple consensus product. There are many different ways of generalization of this basic model. Here, I'll just give you 2 generalizations. The first one is that we could generalize it to 2 groups of competitors, and the second one is that we could have multiple competitors. And the first generation, 2 groups of competitors, suppose that we have 2 groups of the one group have a fixed state at 1, and the other group has fixed state at -1, right? The basic idea is that we could reduce this problem into the 2 competitors problem by combining one group into a supernode and another group into another supernode. Here, of course, we need to change the weights of some links. So we could reduce this problem to this 2 competitors case. But difficult here is that in this 2 group of competitors case, which group will be the winner depends also on the distribution of those competitors in the network. Here, I'll just show you a counterexample to show the difficulties of this case. For example, we still take the Karate Club network as an example. Suppose that we have node 1 and node 34 as 2 competitors. In this case, we could calculate that node 34 is the winner, right? And suppose now that we have node 28 and node 26 as a pair of competitors. In this case, all the other members will support node 28. However, if we put node 34 and 28 as one group, and the nodes 1 and 26 as a large group, we found that, in fact, this group will become the winner. So this shows the difficulties in the two group of competitors case. That's the first generalization. The second generalization is that if we have more than two competitors, for example, if we have three competitors, certainly you cannot just assume that these three competitors have fixed states at 1, 0, -1, because in this case, you break the symmetry of the competitors, right? So one possible ideal is that in this case, we could generalize the states of the competitors from one dimension to a two-dimensional space. That's the basic ideal. That's the basic ideal, right? And in this case, each normal agent will update its states in this vector function, the vector equation. For example, here I just give you an example of 4 competitors case. In this case, we can divide the square into 4 small square. If eventually a normal agent has a steady state located in this small square, it will support competitor 1, and this square support 2, support 3, support 4, right? And we could prove theoretically that the steady states of all the normal agents were definitely nice in the convex Hall of the competitors, right? Here's an example of with 3 competitors. Okay, so just in summary, we did some research on the modeling, prediction, and optimization of competition in complex networks by using knowledges in control theory, which relate to stabilization theory in control, and also using some knowledge from network science and also theoretic science, theoretic computer science. And we know that all this research is still at a very early stages. For example, in fact, our model is still very simple, as we all know that different agents in a network perhaps may have different stubbornness. And also, we might have both cooperation and competition in the model to model the real world case. That's all. Thank you very much. And also, for the last one, I'd like to show you once again the paradise on Earth, very beautiful city of Hangzhou. Thank you very much.
So thank you very much. I really enjoyed this. I was wondering, I'm familiar with some work by, let's say, the economic style, Özdağlar, Acemoglu, in which the modeling, instead of mechanistic and stochastic, is based on models of economic equilibrium. And
yes.
I enjoy both of these approaches, and I'd love your assessment as an expert as to kind of what kinds of questions are appropriate in each of these contexts and what these different methodologies and modeling frameworks, what different things you can learn using these different approaches.
You know, I have a background in control theory. So that's the reason why I propose such a simple model based on the consensus protocol, which means that each agent updates its states just based on the neighbors of the states of its neighbors, right? I'm not very sure how such kind of methods could be applied, for example, in economic and in network. In fact, as you know, there already have been a number of competition models in competitiveness, such as the very classical voter model, right? And ethical model, and a number of models. Here, I think the key point here is that with this model, we could in the future, for example, to incorporate, as I mentioned, the stubbornness, different stubbornness of each agent into the model. For example, we could see how will the distribution of the stubbornness of the agents in the network influence the result. That's just one possibility. Okay, thank you very much.
Thank you.
Yeah.
So I noticed the budget is in terms of the number of nodes and the number of links.
Yes.
So my question is there a measurement of, is there a way we can measure the different costs of different nodes or different links? For example, if NetSci is a competition and I want to win, and my budget is 3, I would like to choose the general chair, the PC chair, and some invited speakers.
Yes.
But it is way easier for me to just make another 3 graduate students to become my supporters.
Yes, yes, yes. That's a very interesting problem. When you try to add some links, how to choose those nodes? Of course, as I mentioned in our works, is that sometimes high degree nodes might not be that important. That's one of our findings. And also, another very important factor is that, in fact, the strength of the links also plays a very important role in the competition. So you need to take care of both the importance of the nodes and the strength of the links. Yeah, that's very important. Thank you very much.
So in the interest of time, we're going to have to cut the questions.
Yes.
But I wanted to make one comment that Phil Menser raised just as you started your talk, and I want to verify if this is true or not. Phil Menser said that this was the first mention of the karate club at NetSci.
Oh, really?
Victoria.
Really?
Phil told me there is a karate club trophy due.
Oh.
At least I know a prior one. It was mentioned by Professor Shweta Bansal during the Satellite meeting on contagion networks on Tuesday, I think, yes. And she was very much looking forward to get the...
Okay.
Do we know who has the karate club trophy? Okay,
All right.
so we'll have to figure this out.
So
Let's
many
thank our
works.
speaker again for
Okay,
that
thank you.
inspiring talk.